So my talk today is on making security invisible, which is kind of like a BuzzFeedy type of title. But basically, you'll see through the talk that it's really just about baking security features into the way that we build infrastructure and making it so that users kind of don't have to think about it and you get secure defaults out of the box. So I'm Jess, if you didn't know that already. I've contributed to a bunch of open source projects, including Docker, Go, Kubernetes, Runtime, and the Linux kernel, and a bunch of small ones, and then I have a bunch on my GitHub, and currently I work at Google doing stuff on Go and Kubernetes. So I have this kind of obsession with sandboxes. Lots of my blog posts are about them, and I just love it. As you can tell from the projects that I contribute to, like Docker and Kubernetes. So what is a sandbox? I think this is the best or funniest description I've seen of one. Whoever came up with sandboxes must not really know how sand works. Because as you can see on the beach, that shit gets everywhere. And then also in a sandbox itself, it's kind of hard to keep inside the box. With little kids and stuff, they just go crazy. So it seems like a kind of counterintuitive term when you really, really deeply think about it. But yeah, it does make sense in a way. So sandboxes provide a net reduction in your attack surface, which is kind of the main definition. So if you compare code execution from inside your sandbox to outside your sandbox, you should be able to ask yourself, are things more possible inside than they are outside? And it should be less possible to do things inside your sandbox than outside the sandbox if you're doing it correctly. If it's more, then I have no idea what you're doing, but that sounds really scary. So yeah. So the most famous of the sandboxes probably, or the most widely used and most protected of vulnerabilities is the Chrome sandbox. So kind of the way this works on different architectures like Linux or Windows or OS X, it's all very different and native to that architecture. But the way it works on Linux is a lot like the way that containers themselves work. So each tab in Chrome actually gets its own PID namespace. But we can go over what a PID namespace is. It's isolation of the process ID space. So the kind of benefit that you get from this is that each tab only knows about itself. So it can't be oh, that other process in this other tab, give me that secret from Facebook or something like that. And I mean, Chrome is daily running arbitrary code execution for you of JavaScript, which is even scarier. So that's why they kind of put these layers together, and that's just one of them. So it also uses unprivileged user namespaces and network namespaces in the newer version of the Linux sandbox. And this is also just like containers, where we use namespaces and C groups. And namespaces are, they limit what a process can see, and C groups actually limit what a process can use. But mostly what Chrome uses is namespaces, because for C groups, you need to be a more privileged user to create them. It's kind of a problem. So you can check out in Chrome your sandbox status and see that you're not running the SUID one, which is the old one. And then you can see all these namespaces. And then what I obviously left out was Seccomp. So it also uses Seccomp, which is the second layer of security there. And this is kind of the main thing we're going to be talking about. So what is Seccomp? It's secure computing with filters. That's kind of where the name comes from, which I didn't know for a long time. It's interesting. And it allows developers to write BPF programs, which we'll also go over, that determine which syscalls can be used, allowed or denied. And you can write whitelists or blacklists, depending on the way that you want to do it, or a combination of both, which is really weird. So BPF is Berkeley packet filters. It's used all throughout the Linux kernel, and it's used for networking and tracing and all this other stuff. And the code is actually pretty simple for it, so a lot of people like to use it because it's less buggy of the other things in the Linux kernel that have all these vulnerabilities and crap because it's so complex. So you're probably why do we care about this really weird shit that's super nerdy? Because I care, and also because it helps with sandboxing and it's nerdy and cool, you'll see. So like one of the first things I did with Seccomp was add Seccomp support to Docker, and this was like in 2015. And the way it first worked was passing a custom profile of like this JSON thing that was basically converted into the BPF filter. And you could say, you know, this syscall is allowed, this syscall is denied. One of the features that wasn't like enabled by default, but that you can do in Seccomp is also trace, which is kind of cool. You could actually like rewrite every single syscall in the kernel to do something else and have like your own user land like networking and shit. But that gets really complex. So this was just custom profiles from the start, and then I added the default Seccomp profile. So if you're ever in Docker and you're just running a container out of the box without privileges or anything, you're gonna get this default profile, and you probably won't even know that it's there. And this was actually one of the harder parts of implementing this because if you look at the date there, it's like December of 2015. So like at that point, you may not know, but a lot of people use Docker, and in production. So setting something as a default that might actually break their existing infrastructure is really hard. So I had like all these like stress nightmares about it, about like breaking literally the world, because we made a whitelist. So we were like just not even putting some syscalls in there. And then I actually like went through all the like public Docker files on GitHub, which there are like a crap ton, and ran through all those to make sure that everything still worked. And then literally the day before the release, I ran like a Skype container on my computer, which if you don't know, like Skype on Linux is 32-bit. And we were missing like two 32-bit syscalls, like of the obscurity. And they were like send and receive, so that's really bad. But luckily we caught it, and then like it was not even as bad as I expected. There was only like one bug after the release, which I was expecting like a shit ton of people being like, my app just broke and everything's e-perming. But yeah, there's just one bug, and it was like some really obscure case, kind of like the Skype on the desktop. So that was really exciting. And this is something you will never see because it is invisible, kind of like going back to the title of the talk. So yeah, Docker's default is a whitelist, and it just specifies all the syscalls that can be allowed. But we blocked like a bunch of stuff by default, like all the bad shit that you wouldn't want regardless. And I'll just go over a few of those, but there's like obviously a ton, and there's an entire list in Docker of like why we block them. But the most interesting ones are like add key, keyctl, and request key. So these all deal with the kernel key ring, which is not actually namespaced. It's only namespaced if you're using user namespaces in conjunction with whatever you're like cloning. So this is kind of like not widely known. A lot of people think that it's namespaced, and it's also almost like this pseudo namespacing where it's like half namespaced and half not, but honestly, like if it's half not, it's really not namespaced. There's like things in proc that you can see that you probably shouldn't be able to, and then if you run keyctl inside a container without a user namespace, you're gonna get some really weird output if you actually have things in your kernel keyring. I also like recently wrote a blog post on this because some random person was building an entire startup around it, and it horrified me. So another one is clone. And this just denies not everything in clone, but cloning new namespaces. So if you're setting the flags for like clone new NS or clone new net, all those things are going to be blocked, which they're already gated by cap sysadmin anyways, except for clone a new user namespace. And there's kind of like this horrifying history with user namespaces and a bunch of vulnerabilities. So we wanted to make sure that you couldn't nest those inside containers. If you look at like the past vulnerabilities of Linux, like a large percentage of them have to deal with ptrace and cloning new user namespaces. And then unshare is kind of for the same exact reasons, because you can get another user namespace and then just do shit. So there was a bunch of other like obsolete syscalls, and then a bunch of 32-bit ones that we didn't need either, and then like some like really weird like reboot and like stuff like that that are blocked as well. So that was fun, but it kind of seems like this could be integrated into more things, and I think a lot of people like don't know about it. So I ended up like obviously taking this into Kubernetes as well, which isn't all that interesting because it's the exact same thing. But then I was like, where else can we like take this? So the first idea I had was something called a bin container, which like actually did more than just like Seccomp stuff. But I'll go over that. So this is like the GitHub, stupid. And then, so this will create like a fully static binary for you with like the rootfs of your container in it. So if you think about how Docker runs today, there's like a Docker daemon, and then you connect to it through an API, and then it spins up your containers. And it's like, that's like pretty heavy. You could actually have just like your binary that contains itself, which is kind of the point of this. And the greatest part of this is it can be run by an unprivileged user because it's using user namespaces, which Docker, if you don't know, runs as root, and that sucks for multi-tenancy. So this just by default would use the same like Docker profile since like I already spent so much time on that. So kind of just to give like an idea of how weird this is, you have your like rootfs for your container, which like, you know, is Debian or Alpine or whatever the hell you choose. And then you compile this into a binary where it's like embedded in it. So I kind of like tarred it up, and then I like compressed it, then I base64 encoded it, then I threw it like literally into the binary itself. So when you run it, it has that like rootfs in it, and it creates this container. And it uses the rootfs as the base of the container. And this is all like just the binary. Like you don't need the daemon, you don't need anything. And then it will set up like Seccomp, AppArmor, SE Linux, and run as an unprivileged user. And then I wrote a blog post on it, and I was like thinking about how runc, which is kind of like what Docker uses internally to spin up containers, should also be starting to be able to be run as unprivileged users. So I emailed the mailing list, and I was like, yo, it's a Sunday. What the fuck am I doing? Stupid shit. So I like wrote down all the things that were like making it break. And a lot of them have to do with C groups, which is also why Chrome doesn't use C groups in their sandbox, because they run everything as unprivileged. Like you don't have to sudo chrome. That would be really weird and horrifying. So there was like a whole discussion over things that need to be added, and then even one person started making kernel patches, which was really cool. Everyone like was super excited about it. And this was like a year ago. Alexa Soray from OpenSUSE, he like opened a patch like right after the mailing list thread, and this was just merged. So it took him like over a year to get this into runc, and it's not even like really fixing the problems with C groups. It's kind of like working around them, but it's really cool that it's in now so people can use it with the exception of C groups until that's fixed in the kernel. So like mad props for waiting a year. Like if you've ever had a patch that took that long, it's the worst. Like I got emails every time he rebased it, and I was just like, wow, that pain is real. So that was one idea, and I was like, meh, it's all right. It's like too heavy. Like you have that entire rootfs. Like I know that I make my Docker images small, like, but there's a bunch of companies that just like 30 gigabytes is like a normal image, and you're not gonna shove that into a binary. So what I do usually is just run static binaries in Docker containers from scratch. So I was like, we don't need this whole rootfs. Like I just want my Go binary to contain itself. So like Dave Cheney and I were talking about this, and he was like, yeah, you could just have like a build flag or something, which like there is, like I work a lot with the Go team, but there was no way I was actually going to propose this to them because it's just a little bit insane. So my terrible idea was like adding this like, if you're familiar with Go, they have like a build mode and like build mode container or something like that. And it would basically allow your Go binary to contain itself, which is pretty cool if you think about it from like a programming language standpoint of like your language will allow you to sandbox your code without you like basically doing anything. So I was like, yay, self-isolating binaries, we can just bake this into Go and protect the entire world. It's like really not that simple though. So yeah, where bin container like took an entire rootfs like this and embedded it in a container, this was taking a static Go binary so that you don't need anything else and embedding that into another binary that would then run in a container. So it looks like this. Like you have your Go code, it creates a static Go binary, and then you're gonna embed that in another binary that you can run with its little like embedded static Go binary. And then that's gonna create your container. Then you're gonna use that like static Go binary with like nothing as a base. And then this time though, since we were already in the Go build mode and we have the linker and we have everything at our disposal, we know your source code, we know everything, you can actually generate like the perfect Seccomp filter so that you know nothing else other than your code will be run, which was kind of the coolest part about this because we have that information. But of course there's like caveats and this is like not as cool as I made it out to be, but for a lot of apps, this would probably work, but just not the weird ones. So the main difference here is the build time generated Seccomp filters, which is kind of the coolest thing. But it still feels heavy, so I was just like, let's take out the container and just do the build time generated Seccomp profile, and then we'll just know that all of our code is covered in this like Seccomp profile. So it's way simpler, and you just get the build mode generated Seccomp filters. So why generate the Seccomp filters at build time? So a lot of people usually do this at runtime, and it's been done in the past like over and over and over again, and it's just not good. Something is always missing when you do this because, you know, like who has 100% test coverage, who actually does all the things that their app is going to do. When you're doing it at runtime, it's never going to actually catch literally all your code and all those little edge cases. So something will break, which then causes your users to just turn it off entirely. This is like the case for like SE Linux and AppArmor, which has like AA Gen Prof. Like all these things don't work. Like there's a proven history of this shit just being turned off. And everyone hates it because they're like, it just stopped working when I did something else. So kind of how this happens is like a user will like start profiling Chrome and they'll be like, yay, AA Gen Prof, like let me do Chrome. And then they'll like click a few tabs and like go through their daily routine or whatever and not like hit everything, but do like what they think is a lot. And then they'll apply this profile to Chrome and reopen Chrome. And then they'll like try to play a video or something that they didn't do the first time. And then it's like, no, you don't have any of that shit. You only have the shit for all that stuff that you did in the first time you were in your tabs. And then that's when they just turn it off. So like runtime generation like never really gets it all. So by generating instead at build time, where we have like literally all your code, we know that nothing will be left out. And we can also find like dead code in Go very easily. So we can definitely leave dead code out, but all the rest you know will be covered. So I wrote a like proof of concept for this, and I showed it at KiwiCon, which was pretty cool. And like I was like, yay, applications can contain themselves. Everything is perfect. The world is great. So there's like a few problems with this building at build time, and like you all might have thought of it while I was saying this. So this is like some Go code, and if you're not familiar with Go, it's just executing this program called my program. So I don't know what the hell my program does, but that's going to become a child process of my main program, and the filters are going to apply to that. So if it calls anything that like I didn't actually use in my code, it's just going to be like, nope, operation not permitted, which really sucks. And there's really not a good way to solve this because I have no idea what that program is. And when I'm building it, it might not even be there. So executing other binaries sucks. And then Go got plugin support in, I think, 1.7. So what this is doing is just opening a plugin, kind of like a DL open. So that plugin might also not be there when I start. Granted, these are built with Go, so there could be like some sort of way to build it into that artifact so that we can grab it. Which could work around this, but it's still like kind of no hold bar. Like it might not even be there. So yeah, this one's another bad one, opening plugins. And then this one's like the most problematic probably of them all. So in Go, you can just call raw syscalls. So like if I just pass a variable to a raw syscall, like you can pretty much do whatever you want. So they have like this one and then raw syscall 6. So yeah, these are kind of like the 3 like edge cases where this won't actually work for generating the perfect profile. But other than this, it's almost perfect. So I think a lot of people don't actually use raw syscall. As long as your app is like not executing something else, you're pretty much good. But it's still not like great. It would be great if we could just like make it entirely invisible and it just worked for everyone. So poop. But yeah, Rome wasn't built in a day. And like Edison made many unsuccessful attempts at inventing the light bulb before he actually did it. So like my dreams of making security actually invisible for things are like not entirely like off base. And I do think there is probably like a future where programming languages will have like sandboxing baked in, because that's kind of almost the layer where you need it. Then you can literally like know exactly what's going to happen and what's going to be called. But yeah, that was pretty much it. I feel like I might have talked too fast. We can do like questions or anything.
Yeah, any questions?
Great stuff, thank you. Does this technique apply only to Go, or did you explore any other options?
Yeah, so I'm most familiar with the Go linker and like how that one works, but I figure other languages like might be able to support it. I'm just not exactly sure how their compile is and like how they do things. But Go, the way the linker works, this was actually easier than I thought it would be. But yeah, the goal was like if I got it to work with Go, I would get it to work with other languages. But since there were such weird caveats, and like I actually exec a lot of other programs in my applications, which is really sad. I was just like, we'll try again and do it a different way, I guess.
Thank you.
Is there some way to get around the exec problem by generating a profile for the things you call out to in exec and maybe merging it with the top level?
Yeah, so I was thinking that, but then we'd go back to the like runtime generation almost, unless it was something built by Go. Then I could like maybe embed like in the header or something, some sort of way to know. But yeah, you're pretty much like back at ground zero at that point. Yeah.
Is there a way to scan the binaries for syscall?
Yeah, I mean, I guess you could like read elf or something, but you're just gonna get like things that you don't necessarily want. It would be hard to generate into, depending on how the binary is compiled, like the exact like syscalls that you want to like then put into the like filter.
Okay, thank you so much, Jess.